Hello everyone, welcome back to the channel. I'm Eric, the workplace safety guy. You use a safety harness every single day working at height and you genuinely believe you're protected. You clip in, you go up, you do the job, and you come back down. And that routine gives you confidence. But here's what I need you to sit with for a moment before we go any further. What if that confidence is based on something that isn't actually true? What if the very equipment you trust with your life has been set up in a way that, during an actual fall, will not perform the way you expect it to? I know that's uncomfortable to hear. I know it might even sound like an exaggeration, but I want you to stay with me, because what I'm about to walk you through today is not my opinion. It's the result of deep research into the most rigorous fall protection standards in the world, OSHA and ANSI, and it's the kind of information that, once it clicks in your head, will permanently change the way you approach every single day of work at height. In 2022, 395 construction workers died from falls in the United States. That number isn't just a statistic. Each one of those 395 is a person who woke up that morning, put on their equipment, went to work, and never came home. And when OSHA investigated those accidents, what they found wasn't that those workers didn't have equipment. What they found, over and over again, was that the equipment was being used incorrectly. A harness worn to loose the lanyard with no energy absorber. An anchor point connected to a structure that had never been tested, never been certified, and never had any business holding a human life. 395 times in a single year. Small mistakes turned into permanent consequences. And fall protection is not just the leading cause of death in construction, it's also the most frequently cited OSHA violation in the entire country. In fiscal year 2023 alone, OSHA cited fall protection violations over 7,000 times. 7,000 times. On 7,000 different job sites, workers were exposed to the exact same risks that killed those 395 people. So today I want to do something about that. I want to take you through the complete system that OSHA requires for working at height, explain every component in real depth, and give you the kind of understanding that goes far beyond just knowing the rules. Because here's something I've learned. Compliance keeps you legal, but understanding keeps you alive. And there's a significant difference between those two things. Let's start from the very beginning. If you're here for the first time, this is where we talk about working at height, fall protection, American safety standards, and everything that goes into doing this work the right way. I don't do surface-level content here. I go deep, I research the actual standards, and I bring you information that you can apply directly on the job. If that's what you're looking for, subscribe right now, because this kind of content comes out every single week and you don't want to miss what's coming next. Now, I want to be honest with you about something. When I first started learning about fall protection standards, I thought I already knew enough. I had been working at height, I wore my harness, I clipped 2 anchor points, I did the job. But the more I read into the actual OSHA regulations and ANSI standards, the more I realized how much I hadn't known. How many details I had been glossing over. How many habits I had developed that felt safe but were actually creating risks I hadn't even considered. That realization was uncomfortable. But it was also one of the most valuable things that ever happened to me professionally. Because once you truly understand how a fall arrest system works, once you understand the physics of what happens to your body during a fall and what each component is actually doing, you stop seeing the equipment as a burden or a checkbox. You start seeing it for what it really is, a precisely engineered system where every element has a specific job to do, and where every mistake has a physical consequence. That's the journey I want to take you on today. Let me start with the foundation of everything. The PFAS, that stands for Personal Fall Arrest System, and it's the framework that OSHA defines in Standard 1926. 502 as the required system for fall protection in most construction and general industry scenarios where there's a risk of falling 6 feet or more. The PFAS is not one thing. It's a system made up of 3 components that must all function together, all be in proper condition, and all be correctly configured at the same time. Those 3 components are the full body harness, the connecting subsystem, which is your lanyard, energy absorber, or self-retracting lifeline, and the anchorage point. Here's the thing about a system. A system is only as strong as its weakest component. I want you to really let that sink in. It doesn't matter if you have a brand new, top-of-the-line harness if your lanyard has no energy absorber. It doesn't matter if your lanyard is perfectly configured if your anchor point can't hold the load. Every single component needs to be right. Every single time, without exception. There's no partial credit in fall protection. The system either works completely or it doesn't work at all. And before I go into each component, I want to establish something that I think is the single most important mental shift you can make when it comes to this kind of work. The PFAS was not designed to prevent you from falling. It was designed to stop your fall before you reach the lower level. The fall is assumed. The system is engineered around the reality that falls happen, and it's designed to respond when they do. Why does that matter? Because when you understand that the fall is assumed, you stop thinking about the equipment as something that makes you invincible. You start thinking about it as something that needs to function perfectly under the absolute worst conditions. And that changes how you inspect it, how you configure it, how you choose your anchor point, and how you think about clearance. It changes everything. Let's talk about the harness first, because this is where I see some of the most persistent and dangerous misunderstandings in the field. The first thing I need to establish clearly is that body belts, the simple waist-only straps that many workers still associate with height safety, are prohibited for use as part of a personal fall arrest system in the United States. OSHA Standard 1926. 502D21 states it without any ambiguity. Body belts shall not be used as part of a personal fall arrest system. That's not a guideline. That's not a recommendation. It's a prohibition, and it exists for a very specific reason. When a fall is arrested, the kinetic energy of your body in motion needs to be transferred somewhere. In a body belt, all of that force concentrates at a single narrow band around your abdomen and lower back. The organs, the spine, the rib cage, all of that is subjected to an enormous, sudden load. Studies have shown that a fall of as little as 2 to 3 meters, arrested by a body belt, can generate enough force to cause vertebral fractures, organ rupture, and internal hemorrhaging. The system stopped the fall. The workers still sustained life-threatening injuries. That's the problem with a body belt, and it's exactly why the full-body harness exists. A full-body harness, compliant with the NSIZ 359.11, distributes the arrest force across a much larger surface area and through a much more resilient structure. The shoulders, chest, pelvis, and thighs all share the load. The force is distributed in a way that the body can actually absorb without catastrophic internal injury. That's the engineering behind it. It's not arbitrary. Every strap, every attachment point, every adjustment is there for a reason. Now, how do I use my harness? Let me walk you through exactly what I do before every single shift at height, because the inspection process is not a formality. It's a genuine assessment of whether this piece of equipment is capable of performing its function today, under the conditions I'll be working in. I start by laying the harness out flat and going through every inch of webbing by hand. I'm not looking from a distance. I'm running my fingers along the material, feeling for anything abnormal. Cuts, abrasions, chemical stains, discoloration, stiffness, brittleness, any of these can indicate that the webbing has been compromised. The thing about webbing damage is that it can be deceptive. A harness can look almost perfect from the outside and have internal degradation that you'll only find by handling it closely. A chemical stain is particularly dangerous because many chemicals attack the synthetic fibers of the webbing without leaving obvious external marks. The strength loss is invisible until the moment it matters most. After the webbing, I inspect every buckle, every D-ring, every rivet, every stitch. Stitching is one of the most critical elements in harness construction because it's what transfers load between components. Stitching at high-stress points, particularly at the dorsal D-ring attachment and the leg loop connections, needs to be intact and unfrayed. Any sign of broken threads, pulled seams, or loose stitching is an immediate out-of-service condition. I don't take chances. I don't evaluate whether it might be okay. If there's any doubt, the harness comes out of service. Once I've done the inspection and the harness passes, I put it on, and here's where a lot of people get careless. Because putting on a harness seems simple, but there are details that matter enormously. The dorsal D-ring, the attachment point on the back, needs to be centered between the shoulder blades, roughly at or slightly below shoulder level. OSHA Standard 1926.502D23 specifies that the attachment point shall be located in the center of the wearer's back near shoulder level or above the wearer's head. This positioning isn't cosmetic. If the D-ring is too low, the geometry of the arrest changes and the force distribution changes with it. You can end up in an inverted or semi-inverted position during and after a fall, which dramatically increases injury risk and sets up the conditions for suspension trauma, which I'll explain in detail later. Every strap gets adjusted until I can fit exactly 2 fingers between the webbing and my body at any point on the harness. Not 1 finger, not 3, 2 fingers. To loose means the harness can shift or the D-ring can migrate during a fall. To tight means restricted circulation and reduced range of motion, which affects how you work and can cause discomfort that leads workers to loosen the harness later in the shift without thinking about the consequences. And no strap can be twisted, ever. A twisted strap doesn't just concentrate stress at the twist point, it also reduces the effective width of the webbing, which reduces its load-bearing capacity. It's a small detail that has a measurable effect on how the harness performs under load. I also want to talk about harness lifespan. Most manufacturers recommend removing a harness from service after 5 years from the date of first use, regardless of its visual condition. Synthetic materials degrade over time through UV exposure, humidity, temperature, cycling, and the simple stress of daily use. A harness that looks clean and intact can have significantly reduced strength if it's been in service for several years. Know the manufacture date of your harness. Know the first use date. and follow the manufacturer's retirement guidelines without exception. Now let's get into the lanyard, which is in many ways the most technically misunderstood component of the entire system. The lanyard is what connects your harness to the anchorage point. It sounds like a simple link, but the engineering behind a proper lanyard and the physics of what happens when it has to do its job is something most workers have never been fully walked through. So let me do that right now. When you fall, your body accelerates downward under gravity. In 6 feet of free fall, the maximum OSHA allows under standard 1926, 502 de 16, you will be traveling at roughly 13 to 14 miles per hour when the lanyard reaches its full extension and begins to arrest the fall. At that point, your body needs to decelerate from 13 to 14 miles per hour to 0 in a very short distance. The force generated by that deceleration is what we call the maximum arrest force, or MAF. Without an energy absorber, a 6-foot free fall can generate arrest forces exceeding 2,000 pounds on the body. Let me put that into perspective for you. 2,000 pounds is roughly the weight of a full-size sedan. Imagine having that force applied to your body in a fraction of a second. The consequences include vertebral compression fractures, torn ligaments, cracked ribs, internal bleeding, and severe neck injuries, all potentially resulting from a fall that the system technically stopped. The system did its job, but without an energy absorber, it did it in a way that the human body cannot withstand. ANSIZ 359.13 addresses this directly. It requires that energy absorbers used in fall arrest systems limit the maximum arrest force to 900 pounds, force or less. The way an energy absorber achieves this is through a process of controlled tearing. Inside the energy absorber pack is a length of webbing that has been specially stitched in a folded or packed configuration. When the arrest force exceeds a certain threshold, those stitches begin to tear in sequence, extending the stopping distance by 3 to 4.5 additional feet. That extended stopping distance is what converts an abrupt, violent deceleration into a slower, more survivable one. The same energy is absorbed. The absorber just buys more time and distance to absorb it. 900 pounds is still a tremendous force, but it's a force that the human body, properly supported in a correctly fitted full-body harness, can absorb without permanent injury. 2,000 pounds is not. When I see a worker using a lanyard without an energy absorber, I stop the work immediately. Not because I'm trying to enforce a rule. Because that worker genuinely believes they are protected when they are not. They have the appearance of a fall arrest system without the actual capability of one. That false confidence is more dangerous than having no system at all, because it removes the instinct to be cautious. Now I want to talk about something that I think is one of the most underappreciated concepts in all of fall protection: total fall distance. And I want to be precise here, because this is where I see even safety-conscious workers make dangerous assumptions. Most workers know they're using a 6-foot lanyard, so they assume their fall distance is 6 feet. But total fall distance is a calculation, not a single measurement, and it goes like this. You start with the free fall distance, which is the distance from your anchor point down to your dorsal deering at the moment of the fall. If you're anchored at chest level, your deering might be a foot or two below the anchor before you even start falling, which adds to your free fall distance. Then you add the full length of the lanyard, 6 feet. Then you add the energy absorber deployment distance, up to 4.5 feet. Then you add the distance from your deering down to your feet, roughly 5 feet for the average worker. Then you add a safety margin. When you do that math, a standard 6-foot lanyard can result in a total fall distance of 18 to 20 feet in some configurations. If there are only 15 feet of clearance between your work position and the structure or ground below you, the system will not stop you before impact. You will hit, and at that point, it doesn't matter that the harness was perfect and the lanyard had an energy absorber. The clearance calculation was wrong, and the system failed. This is why I calculate clearance before I anchor. Every single time, I look at where I'm anchoring, I look at what's below me, and I make sure the math works before I ever start the job. It's not a complicated calculation once you understand it, but it requires you to actually do it rather than assume everything is fine because you're wearing equipment. For environments with limited clearance, the answer is a self-retracting lifeline, which ANSI 359.14 covers comprehensively. A properly rated self-retracting device engages within 2 feet of free fall, dramatically shorter than a standard lanyard, and limits total fall distance to a fraction of what a conventional lanyard allows. In tight clearance situations, a self-retracting lifeline isn't a luxury. It's the only way to build a system that actually works, given the geometry of the environment. And then there's the Y-lanyard, which I use when a job requires me to move between anchor points. The Y-lanyard has 2 legs, which means I can connect one leg to a new anchor before disconnecting the old one. The rule I follow without exception. I never disconnect one leg until the other is already connected. Never. There is no situation urgent enough. No task important enough. No conversation distracting enough to justify being unconnected at height. If I'm between connections, I'm unprotected. That is never acceptable. Now we arrive at the component that, in my experience, causes more fatal accidents than the other two combined. Not because it's more complicated, but because the mistakes made here are less visible and the consequences of those mistakes are absolute. The anchorage point. I want you to hear what I'm about to say very clearly. The anchorage point is the element that everything else in the system depends on. It's the point where the entire load of an arrested fall ultimately lands. If it fails, nothing else matters. The harness doesn't help. The energy absorber doesn't help. The self-retracting lifeline doesn't help. You fall, and nothing stops you. OSHA, Standard 1926.502 D15, states that anchorage points must be capable of supporting at least 5,000 pounds per attached worker, or be designed as part of a complete personal fall arrest system that maintains a safety factor of at least 2, under the supervision of a qualified person. 5,000 pounds is the benchmark. That's not a conservative estimate built on guesswork. It's the result of engineering analysis of worst-case fall arrest forces with appropriate safety margins built in. If a structure cannot hold 5,000 pounds of suddenly applied dynamic load, it is not an acceptable anchorage point. Full stop. Now here's where I want to get very honest with you about what I see in the field. Because this is where the gap between what the standard says and what actually happens on job sites is the widest. I have seen workers anchor to handrails. I have seen workers clip to hydraulic piping. I have seen workers tie off to conduit. I have seen workers attach their lanyards to scaffolding uprights that were themselves sitting on unsecured planks. I have seen workers use equipment lifting lugs, D-rings, designed for rigging loads, not for human fall arrest, as anchor points, and in every one of those cases, the worker genuinely believed they were protected because they were attached to something. The connection existed. But the connection was not an anchorage point. It was a structure that had never been evaluated, never been tested, and never been certified to hold 5,000 pounds of dynamic load. The dangerous thing about improper anchor points is that they rarely fail during normal use. You can clip to a handrail 100 times and it holds perfectly because you're never asking it to hold 5,000 pounds of dynamic load. But on that one day when you fall, when that force is actually applied, the handrail fails. And then the investigation shows that the handrail was never rated for that use, was never intended for that use, and that the worker's death was entirely preventable. The anchorage points I use are certified structural steel members that I have verified are part of the primary structural system of the building. Certified anchor connectors or anchor slings rated for fall arrest use. Engineered horizontal lifeline systems installed in accordance with ANSI Z359.15, Z359.16, or Z359.17, and dedicated anchor points designed by a licensed engineer specifically for personal fall arrest. If a structure doesn't fall clearly within one of those categories, I don't use it. No exceptions. No matter how solid it looks, no matter how convenient it would be. If I can't verify that it's rated for the load, it's not my anchor point. And I want to talk about something that very few people discuss when it comes to anchorage selection. The position of the anchor relative to where I'm working. Because this isn't just about whether the anchor can hold the load. It's also about the geometry of what happens when I fall. The first reason I always try to anchor above my head is straightforward physics. The higher my anchor point is above me, the shorter my free fall distance before the lanyard begins to tension. If my anchor is at head height and I fall, my free fall before the lanyard begins to engage is minimal. If my anchor is at chest height, I'm already adding several feet of free fall before the lanyard even starts to tighten. Every foot of additional free fall increases both the velocity I reach before arrest and the total force generated during arrest. Anchor high, always. The second reason is something called a swing fall, and this is a hazard that I genuinely believe doesn't receive enough attention in fall protection training. A swing fall occurs when a worker is not positioned directly below their anchor point at the moment of a fall. Instead of falling straight down, the physics of the situation cause the worker to swing in a pendulum arc toward the point directly below the anchor. During that pendulum swing, the worker can reach speeds of up to 14 miles per hour and can strike walls, structural members, equipment, or any other obstacle in the arc path. The injury potential from that impact is severe, and it occurs entirely independently of whatever force the harness and lanyard were managing during the arrest. I position myself as close to directly below my anchor as possible. When that's not achievable, I use multiple anchor points to limit the potential swing arc. When the geometry of the workspace makes swing fall risk significant, I factor that into my entire work plan. It's not an afterthought. It's part of how I set up the job from the beginning. Now I want to take a few minutes to talk about something that happens after the fall. After the system has done its job, and after the worker is hanging suspended in the harness. I want to talk about suspension trauma. Because this is the part of fall protection that almost never gets discussed in training, and it can kill a worker even when everything else went exactly right. Suspension trauma, also called harness hang syndrome or orthostatic intolerance, develops when a person is suspended motionless in a harness after a fall arrest. Here's what happens in the body. The leg straps of the harness compress the major blood vessels in the legs, restricting venous return, the flow of blood from the legs back up to the heart. Blood begins to pool in the lower limbs. The heart is working against a reduced blood supply. The brain is receiving less oxygenated blood. Within 3 to 5 minutes of motionless suspension, some workers begin experiencing dizziness, nausea, weakness, and visual disturbances. Within minutes more, some lose consciousness. An OSHA safety bulletin on suspension trauma is explicit. Death can occur within 30 minutes if the worker is not rescued. Let that sink in for a moment. Your system worked perfectly. The fall was arrested. You're hanging in the air, uninjured from the fall itself. And you can still die, not from the fall, but from hanging too long afterward. This is why OSHA requires that every at-height work plan include a rescue plan, established before work begins, not improvised after an accident. Before, the rescue plan needs to identify who will perform the rescue, what equipment will be used, and how quickly rescue can realistically be achieved. If rescue cannot be achieved within a few minutes, the rescue plan is not adequate. And there's one more detail that rescuers absolutely must know. When a suspended worker is brought down, the instinct is to lay them flat so they can rest and recover. But laying a suspension trauma victim flat can trigger something called reflow syndrome. The blood that has been pooled in the legs suddenly rushes back to the heart in a rapid, uncontrolled surge, and the cardiovascular system can go into shock. Cardiac arrest is a real and documented risk. The correct approach is to keep the rescued worker in an upright seated position with the knees slightly bent, supporting blood return gradually rather than all at once, while emergency medical services are contacted immediately. This is the kind of detail that doesn't show up in a basic fall protection orientation. It's the kind of knowledge that lives in the space between having the right equipment and actually understanding the complete picture of what can go wrong. And it's the kind of knowledge that, in the right moment, saves a life. Let me walk through what I consider the most common and most dangerous mistakes I see when it comes to the complete fall protection system, because knowing what goes wrong is just as important as knowing what to do right. The first mistake is skipping the pre-use inspection. I understand that workdays are busy and that inspecting equipment before every single shift can feel like one more thing on an already long list. But OSHA Standard 1926.502D17 requires pre-use inspection for a reason. Equipment can be damaged during use, and the damage isn't always obvious. A harness that was fine yesterday can have been subjected to a minor chemical splash, an abrasion against a rough edge, or an impact that wasn't recognized as significant. The inspection is the only way to know that the equipment is actually in the condition you're assuming it's in. Skip it, and you're trusting something you haven't verified. The second mistake is using lanyards without energy absorbers. I've addressed this in detail already, but I want to reinforce it here because it's still widespread. The cost difference between a lanyard with an energy absorber and one without is relatively small. The performance difference in an actual fall is the difference between a survivable arrest force and one that causes catastrophic injury. There is no valid argument for using a lanyard without an energy absorber in a fall arrest system. None. The third mistake is what I call false anchorage, connecting to a point that looks like a valid anchor without verifying that it actually is one. I've described what I see in the field: handrails, piping, conduit, scaffolding, equipment rings. None of these are fall arrest anchor points unless they have been specifically evaluated, tested, and certified as such. Looking solid and being rated for 5,000 pounds of dynamic load are two completely different things, and only one of them matters. The fourth mistake is failing to calculate total fall clearance before anchoring. I know I've been through this calculation already, but I want to emphasize it once more because it's a mistake that kills. A 6-foot lanyard does not mean a 6-foot fall. Total fall distance in many configurations exceeds 18 feet. If you don't have that clearance below your work position, you need a different anchor point, a shorter connecting device, or a self-retracting lifeline. The clearance calculation has to happen before the work begins, not after you've already set up and started the job. The fifth mistake is not having a rescue plan. This one is often overlooked because it's hard to think about. Nobody wants to plan for the possibility that someone on their crew is going to fall. But that's exactly when the planning needs to happen, before it's needed. A rescue plan that doesn't exist until the moment of an accident is not a rescue plan. It's improvisation. An improvisation during a suspension trauma emergency, where minutes matter, costs lives. I want to close today with something that I think matters more than any specific standard or regulation I've cited. I want to talk about the difference between compliance and genuine safety culture, because understanding that difference is, in my experience, what separates job sites that have accidents from job sites that don't. Compliance means doing what the standard requires because there are consequences for not doing it. Inspections happen because OSHA might show up. Anchor points get evaluated because the safety officer is watching. Equipment gets worn correctly because the supervisor is on site. The standard drives the behavior, and when the external pressure is removed, the behavior changes. Safety culture means doing what's right because you understand why it's right. You inspect your harness because you know exactly what a damaged steering attachment point would mean during a fall arrest. You calculate your clearance because you know the math of total fall distance, and you know what happens when that math doesn't work. You refuse to anchor to an uncertified point because you understand what 5,000 pounds of dynamic load actually means, and you know that a handrail was never designed to hold it. The difference between those two mindsets is not just philosophical, it's measurable. Compliance-driven safety relies on external enforcement. It has gaps wherever oversight is absent. Safety culture is self-sustaining. It functions the same way whether anyone is watching or not, because the motivation isn't avoiding consequences, it's understanding what's at stake. When I read the OSHA standards, I'm not reading a list of rules. I'm reading a document that was written from the accumulated evidence of real accidents. Every specific number in those standards represents an engineering boundary that was established through analysis of what happens when that boundary is crossed. The 5,000-pound anchorage requirement isn't arbitrary. It's derived from analysis of the worst-case forces a fall arrest system can generate. The prohibition of body belts isn't an overreach. It's the result of documented evidence of the injuries they cause. The energy absorber requirement isn't excessive caution, it's the result of biomechanical research into what forces the human body can actually tolerate. Every standard is a lesson written from an accident. When I understand that, I stop looking for the minimum I can do to comply, and I start looking for the level of understanding and care that the people who wrote those standards were trying to describe, because they were trying to prevent the next accident. And so am I, so let me bring everything together one final time, before I leave you with the PFAS, the Personal Fall Arrest System, is a three-component system where every element must be correct, in good condition, and properly configured at the same time. The full-body harness, compliant with ANSI 359.11, must be inspected before every use, worn correctly with the dorsal gearing in the right position, and adjusted to proper fit with no twisted or loose straps. Body belts are prohibited for fall arrest. Harnesses have a service life. Know yours. The lanyard or connecting subsystem must include an energy absorber that limits the maximum arrest force on your body to 900 pounds force or less, as required by ANSI 359.13. Total fall distance must be calculated every time, accounting for lanyard length, absorber deployment, during 2-foot distance, and clearance margin. When clearance is limited, a self-retracting lifeline compliant with a NSIZ 359.14 is the appropriate tool. Y-lanyards provide continuous connection during movement, but the rule of never being disconnected must be maintained at all times. The anchorage point must be capable of supporting a minimum of 5,000 pounds per attached worker, as required by OSHA 1926.502 D15. Only use certified structural members, engineered anchor systems, or dedicated anchor points designed by a licensed professional. Position anchors as high as possible to minimize free fall distance and swing fall risk. Never anchor to handrails, piping, conduit, unsecured scaffolding, or any structure not specifically rated for fall arrest. After a fall arrest, rescue must be rapid and informed. Suspension trauma can develop within minutes. Workers should be kept in an upright seated position after rescue. Emergency medical services must be contacted immediately. Rescue plans must exist before work begins, not after. Safety at height is not about wearing equipment. It's about understanding a system, respecting physics, and never negotiating with risk, because gravity doesn't negotiate with you. If this video gave you something real, a new understanding, a detail you hadn't considered, a calculation you hadn't done, then do me a favor right now. Hit the like button. That one action tells the algorithm this content is worth showing to other workers who need it. And I genuinely believe this information needs to reach as many people in this industry as possible. Share this video with your crew, with your supervisor, with anyone who works at height. Not because it's required, because it matters. Subscribe to this channel if you want to keep going deeper. I have upcoming videos on pre-use equipment inspection step-by-step, real OSHA, HLIT documented anchorage failures and what caused them, and a complete breakdown of self-retracting lifelines and how to choose the right one for your environment. You don't want to miss those. And drop something in the comments. What's the most dangerous fall protection mistake you've seen on a job site? Or, if you're newer to this, what part of today's video gave you the most to think about? I read every comment, and your experiences have a way of becoming the next video on this channel. Stay sharp, stay connected. I'll see you in the next one.